Hello, my name is Juarez Monteiro and today I will present our work titled Augmented Behavioral Cloning from Observation. The paper was made in partnership with the following authors: Juarez Monteiro, Nathan Gavensky, Roger Granada, Felipe Mendeguzzi, and Rodrigo Barros. Imitation from observation is a computational technique that teaches an agent on how to mimic an expert's behavior by observing only the sequence of states from the expert demonstrations. Recent approaches learn the inverse dynamics of the environment and an imitation policy by interleaving epochs of both models while changing the demonstration data. However, such approaches often get stuck into suboptimal solutions that are distant from the expert, limiting their imitation effectiveness. We address this problem with a novel approach that overcomes the problem of reaching bad local minima by exploring a self-attention mechanism that better captures global features of the states and a sampling strategy that regulates the observations that are used for learning. Behavior cloning from observation, proposed by Torabi, combines both an inverse dynamics model to infer actions in a self-supervised fashion, and a policy model, which is a function that tells the agent what to do in each possible state of the environment. The former considers the problem of learning the agent-specific inverse dynamics, and the latter considers the problem of learning an imitation policy from a set of demonstration trajectories. We detail both components as well as the modifications to this framework we proposed in this paper. We model the inverse dynamics model, or IDM, as a neural network responsible for learning the actions that make the agent transition from state ST to ST plus 1. In order to learn these actions without supervision, the agent interacts with the environment using a random policy, generating pairs of states to train a specific agent. We store pairs of states along with their corresponding action as a pre-demonstration. At test time, the IDM uses the learned parameters to predict an action given a state transition. We augment the original IDM by adding the self-attention module, which we use to compensate for the large variation of the samples in the iterative process. The self-attention forces the IDM to identify what is essential to learn from each state. When using self-attention with images, it can identify which part of the image representation of the state is essential for predicting the correct action. The policy model is responsible for cloning the expert's behavior. Based on the expert demonstrations, where each demonstration comprises pairs of subsequent states, our approach uses the IDM to compute the distribution over actions and predict action that corresponds to the movement made by the expert to change from the state ST to ST plus 1. With the predicted action, the method builds a set of state-action pairs corresponding to the action taking the state St. Then, this is used to learn the imitation policy that mimics the expert behavior in a supervised fashion. Compared to the original BCO, we augment the policy model by adding a self-attention module. Unlike in the IDM, we use self-attention to reduce the state changes during each iteration, since the self-attention module focuses on small details and differentiates better all classes given by the IDM. The self-attention also allows the policy to look non-locally at the states, helping the model to learn faster for higher dimensional with a more gradual success rate in between iterations. The problem of the iterated BCO is that it only uses the set of post-demonstrations to retrain the IDM. Thus, for those cases in which the policy still does not have good enough predictive performance, the generated set of post-demonstrations will contain misleading actions for specific pairs of states. In order to deal with these problems, we create a model that iteratively improves over ABCO via sampling method that weights how much the IDM should learn from pre-demonstrations and post-demonstrations. Unlike the work proposed by Torabi, which uses only pre-demonstrations to train the IDM, our work updates its pre-demonstration data in every iteration. In order to evaluate our approach, we compare our trained models with the state-of-the-art approach in 4 different environments. In this table, we show the results in terms of average episodic reward and performance for our models and the related work. For comparison purposes, we also show the result for behavioral clone, which is a supervised approach. We show that our method is equal or surpasses the state-of-the-art approaches in all of the environments but the maze 3x3, where results are similar to BCO. The overall results confirm that the attention module and our sampling strategy can improve the imitation process. Although in all the maze environments we achieved the highest score performance, we can observe that as the complexity of the environment increases, our performance decreases. However, we can see in the results that ABCO is less affected than BCO as the complexity increases. We would like to thank and mention that this study was financed in part by the CAPES Brazil and CAPES Papergues agreement. We gratefully acknowledge the support of NVIDIA Corporation with the donation of the graphic cards used for this research. Thank you for watching.